click on that button there. And we are rolling.
All right.
All right. So I'm going to go ahead and take control of the screen. Let me go ahead and share my desktop here. All right, so I'm going to pin the video. Let's go about like that. So there is, I actually haven't watched the past few recordings, but there was some feedback that was a little disorienting to have the camera or the focus bounce around based on who was talking when someone was presenting. So I think I've fixed that. I'll go and set this up in the corner. And so let me show you what I've been working on. First off, as I had mentioned, we have been posting our, for those of you who didn't already know or notice, we have been posting each of our weekly talks on our RSSC Robotics webpage. They are under RSSC Robotics, playlists, RSSC Talks, and they're also listed by date as we do them. So I'm trying to grab a nice screenshot or a capture to kind of get the essence of what the talk was about. And Walter already did a great job of updating the website. With the links to the same. So I think it's going pretty well. At some point, I may even try to sneak a link or a mention in through Reddit for the playlist for the past meetings to try to drum up some more membership. One of the things that also came up, and I'll just mention it again. Sorry for everyone else on the call who was part of the original conversation. Is there was the subject of how much outreach did we want to do with the Zoom meetings? And we'll talk about two extremes. I know I lie on one side of this, but just so you know, this conversation happened. On one side, there was the, hey, let's just keep the Zoom meetings to our club members because above a certain number of people, it becomes less a community event and more a let's all log in and watch someone talk for an hour and then log off because there's no way to cross communicate or chat with other people because there's so many people. And that's kind of the direction we're leaning towards now. So if you're a member of one of our clubs and you're part of our distribution list, then you get the notice about it. And then of course you're welcome to join. And we have between 20 and 30 people join in every time, which is about perfect from a community perspective because there's still not so many people that you can private chat and you can get a look at everyone's face and you know who else is here. That's kind of the format we've decided to move forward with. The other way of doing this, which we talked about and we're not excited about doing, was to publicize the meetings in advance on every social media possible to get as many people to join and be awesome and famous and world renowned for highly technical weekly meetings. But at that point, it's no longer a community event. It's not just us. It turns into this whole other thing, and we kind of lose that sense of, hey, this is for us to catch up with our people and see. So as a result of that conversation, we'll probably decide to publicize the archive of each of our previous talks so anyone can go in and download them, but we'll keep the live talks just for our peeps, our guys and gals that belong to our three clubs. Okay, so on that note, Alan, I've always promised that I'm happy to talk about whatever I'm working on from week to week. And this past week, one of my older projects that I never finished came back and tapped me on the shoulder. So a few years ago, there's a super smart guy named Paul Gould that actually won the 2018 award on Hackaday for innovative projects for this 3D printed cycloidal gear reducer. So it's a gearbox, and he designed the entire thing himself. Everything's either 3D printed except for the bearings, and he uses a brushless DC motor. And the box you're looking at here is, I think it's a 25-to-1 gear reduction. Let me go ahead and get a piece of the internals here. And what's nice about it is it, compared to the ones I'm going to show you in a few minutes, it's low cost. There's a lot of fiddly bits in the first generation gearbox. It's quite an undertaking to create one, but overall it's not very expensive. It has a 25-to-1 gear reduction. As long as you can print things out relatively accurately, it is low backlash and lightweight and very powerful for its size and its weight. And so I've been playing with this concept on and off for about the past 2 years, and then something shiny came along and I dropped it for a while. But this one you're looking here, this earlier example, with 12-volt power supply, 5 amps, is able to provide a force of about 10 Newton meters. And this brushless motor and this cycloidal gearbox isn't operating anywhere near at its max. He's only giving it about 1/4 of the total power. And I don't think he's done any destructive testing, but the point is these things are small and potentially very powerful. It sounds like a lot of fun. So a couple of things have happened since then. This is from late 2018. Boston Dynamics Spot Mini, I'm sure everyone's seen, and it's been on my Christmas list for the past couple of years. And there's another set of people out there, MIT. They've built this thing called the MIT Cheetah. And they've published all of their work, all of their design. I don't know much about the mechanics of the Spot Mini, but they've published a lot of information about the Cheetah actuator. And let me go ahead and dig in this a little bit. So this is how they're doing it. It's a very wide and shallow brushless motor, and you know, they're a lot more complicated than the normal motors, but potentially a lot more powerful based on their weight and their size. And in this big space in the middle, they put a 6-to-1 planetary gear reducer, just right smack dab in the middle of the brushless motor. And then they use these aluminum framing components on the outside to mount it to stuff. The entire motor is very narrow and very strong, and really impressive. These are smaller versions of the Spot Mini. I did not think ahead to get a video clip of it for people that have not seen the Spot Mini before, or sorry, the MIT Cheetah before. But for those of you who have not, it's smaller. It doesn't look to be as complicated. It's more of a project than a product right now, but it seems to have all the same walking capabilities that the Spot Mini does. So super cool. If you Google search or YouTube search, you'll find some people who are reproducing this. And so this guy's been in various stages of development for the past couple of years as well. Agile, adept, quick, just a lot of fun. So, and there's some additional papers on how they do what they do. Now, something very interesting came up when they started publishing designs about this, and it's kind of all wrapped up in the same kind of concept. You want something strong, you want something light, and we've been able to do that since honestly the mid-'80s with standard gear reductions and powerful motors. The thing that has been a lot harder to do is to intuit how much force you're applying. So it's one thing to apply power to a motor and exert a force and have things move around, but it's quite a whole other ballgame to say, okay, how much force am I applying? Because you can calculate out, if you know the position of something, you can calculate out over time your speed, your acceleration for second order derivatives. You can characterize everything about the motion, but between load sensors, force sensitive resistors, there's really not a lot you can do to identify your static load or how much force you're applying. And you can approximate it by like using a current sensor, uh, but it's inexact because depending on how high your gearing is, and a lot of these super powerful motors have very high gearing, you have, inertia is not the right word, but there's a certain minimum force that you have to be able to apply before that's enough force to backdrive it. So that minimum amount of force represents the lightest force that you could conceivably measure on the gearbox, and that's just the way things were. Now, fast forward to right now, we've got some really cool designs out there, MIT Cheetah, Spot Mini. Now, on the MIT Cheetah, let me switch back over to this guy right here. I had mentioned that there was a 6-to-1 planetary gear reduction that was stuck in the middle. And so what they figured out was that if they use a very low gear reduction, 6-to-1 is actually almost nothing compared to like a 20, 30, 40-to-1, where so you could use a smaller motor and you could push a lot more weight, exert a lot more force, but do it more slowly. They went the other way and said, okay, we're going to look for the minimum gear reduction possible and pair it up with a really big, really wide brushless motor. And when you design gearboxes that way, it actually doesn't take much force at all to backdrive it. So, you know, you turn the input shaft and the output goes, turn the output shaft and the input shaft spins really fast. If the gear reduction is really low and the gears are well made, it doesn't take a lot of force to move it, which means
Alan,
that it takes a lot less force to maintain a position. You can then use standard current sensing or some other technology to approximate the amount of force that your gearbox is expressing. And you can also move a lot faster. So that's one of the pieces of magic in the MIT Cheetah actuator. And it got me excited about these hypocycloidal gears, thinking, well, what if I could adapt the hypocycloidal design to a low ratio gearbox? Could I get something similar? So I got back into it. And just after I started designing, oh, sorry.
What I'm a little, you know, I don't know much about these type of about motors in general, but what's the main use of the back driving? Is that if you're on a hill or something, or if there's force being applied by the environment that the system can tell?
Well, yeah, no, it's a good question. So, and it all gets back to how do you sense how much force you're exerting? How can you, and then what kind of information do you get back? So when you have a gearbox, normally you'll spin the input shaft, and you know, if it's a 20-to-1, every 20 rotations of the input shaft, the output shaft will go around once, right? So that's a 21 gear reduction. Usually they're planetary gear reductions. And for anyone that's, and I'm going to show you my cycloidal stuff in a second, but generally speaking, when you twist it forwards, you know, you put in the input shaft, you can twist it really easily, and then you end up trading speed for torque. And so if it's a 20-to-1, it'll minus frictional inefficiencies. If it's a 21 gear reduction, it'll spin 1/20th as fast, but with 20 times the force, right? That's the whole purpose between gear reductions. You're trading speed for additional force. But if you end up trying to turn it backwards, you'll notice that it's a lot harder to turn the output shaft to make the input shaft twist, because if you twist your output shaft around once and it was a 20-to-1 gear reduction, if you twist it around once, that means the input shaft is spun 20 times, right? Because of the 20-to-1 gear reduction. And it's a lot harder to twist. So the higher the gear reduction, the more force you have to apply on the output shaft to sample, let's just call it friction, how much friction occurs in the gearbox. And so if it takes 7 pounds of force, let's say, not great units, but if it takes 10 pounds of force to twist that output shaft at all, that means that the minimum force that you can sense is 10 pounds, right? Because anything pushing up against it, the output shaft won't even twist the input shaft, so there's nothing for it to hold on to. So it's one of the trade-offs in trying to figure out, how do I sense how hard I'm pushing on the ground, or how hard the leg is moving, or how much force is being applied to swing that leg over an arc of motion. The lower the gear ratio, the less output force is required to turn the input shaft, and then the more sensitive your you can then do things like use current sensing to approximate how much force is being applied to the output shaft. Is that any clearer, or is that clear as mud?
Yeah, that's enlightening. Yeah, I understand.
Okay. Yeah, sorry about that. I've been reading up on. I've been like an armchair cycloidal gear reduction guy for the past couple of years, and I barely understand it myself. So yeah, thanks for calling me on it. And so to come full circle, it's okay. Can I 3D print a hypocycloidal gear in design with a low gear ratio, and then do you still get that same payoff? Oh, my mom's calling. Let me go ahead and I'll call her back later. Hi, Mom. Get some of that payoff for a smaller actuator. So with this introduction, this is kind of why I'm doing what I'm doing this month. And for anyone who would like to build their own MIT Cheetah, but you know, doesn't go to MIT, just so you're aware, they've AliExpress sells these gearboxes now, which are an exact reproduction of the same design for $300 to $360. They're $300 for just the motor and gearbox. If it includes the drive electronics, it's $350, which is still a pretty good deal. It's out of my price range. You need 12 of them to do an MIT Cheetah. And just recently, they've started to sell completely assembled MIT Cheetah designs. So the stuff is out there and it works. It's pretty cool and coming down in price. Still too expensive for me, so I'm trying to see if I can approximate something with 3D printed hypocycloidal gears that maybe won't burn up or melt.
Quick question, Alan. The
Yeah.
MIT Cheetah that you can buy off of AliExpress, does that include the software as well? Is that like a full package? Is that like the real? Is that 100% faithful replication of the MIT Cheetah? Do you know?
Oh, they can't deliver to the United States. I wonder why. You know, I know very little about these people that are selling these. I don't want to call them pirated copies, but these aren't MIT approved reproductions of them. I doubt. Oh, there's an operating system on it. So it looks like they're including some sort of software package. I haven't checked up to see what MIT has published on it or what they're doing. Apparently you need, oh, you get one 3,000 watt adjustable power supply. That's pretty beefy. But you know, the manufacturer quality looks pretty good. These are, what do you think? These are cast aluminum parts. So yeah, anyone with a spare 12 grand plus change and can ship to an intermediate country on the way here. I can get it in gray too. That's pretty cool.
Have it go to the Cayman Islands and.
All right. So these guys won't ship to the U.S. How about these guys? Oh, yep, these guys will ship to the U.S. So that looks like so much fun. If I had a spare 13 grand burning a hole in my pocket, build your own robot.
It's a knockoff, but but the quality might be reasonable. All those parts.
Yeah, it looks pretty good. So with all that as a background, here's why I'm doing what I'm doing today. There have been other people on YouTube and instructions on how to design hypocycloidal gears, either by recreating the hypocycloidal path and then plotting that out over time, or using some stuff in Fusion 360 to do that. So I've done both of these, and I'm not going to bore you with them. They're super tedious, but they work. When I was watching this guy's video a few weeks ago, in the comment section, someone came out and said, hey, why don't you just use the cycloidal gear solver on GitHub And the comments aren't coming up right now, so we'll skip that part. And lo and behold, 4 years ago, someone wrote and published a cycloidal gear generator in Visual Basic, I think. And so what I did is I went ahead and grabbed that. And sure enough, you can plug in all these different parameters, the roller distance between the center of the gear and the outside, the number of teeth, the radius of the rollers, to create a hypocycloidal gear profile that you can then import as a DXF file. Super awesome. So now I can think, right? So I can go in and say, okay, what would 10:1 look like? What would it look like if I increase the diameter by 2 millimeters? Instead of plotting it out over the course of 30 minutes every time I had a change, you can just use the calculator and then export that solution as a DXF. I'll just save that one as RSSC. So far, so good. Love that. Now, on the Fusion 360 side, pretty much all you have to do, and the point of this talk is symmetry, drawing, extrusion. This is just all the build-up to kind of a little window into what I do sometimes. Let's go ahead and create a new sketch. Now, just from experience, I know that the reference diameter of my gearbox, let's go ahead and make that 50 millimeters. Let's go and go dimension and do that. Oh, let's let me show you something really quick. Now, on the screen, can you see my chat? Can you see my video window? Am I moving that to the center? Can you see that?
Only
Okay.
We can't see your video window, but we can see the video window that Zoom provides at the top.
Okay. All right, so let's do this. So am I front and center now? I should have pinned my video. Did that work?
Your video is front and center.
Okay.
Yeah. Your face is front and center.
All right. Small, real pretty. All right. So to skip to the end first, I'm going to go ahead and move the camera down so you can kind of see what I'm working on now. So this is an example of the hypocycloidal gear that I'm going to show you in Fusion. So this week I did a couple of designs. I printed things out. The tolerances on this one aren't great because I rushed it, but in principle it absolutely works. So let me show you what's going on here, and I'm going to show you each of the components until we get bored on the live stream. But here in the center, you can see the input shaft. I drew a little arrow with a Sharpie. And on the outside, I drew a little marker so you could see the progression of the output shaft. Now in the middle there are these hypocycloidal gears, and I added in a little reference mark right here so that you could kind of see how all three of these work together. Now this is a 6:1 hypocycloidal gear reducer, which means that for every 6 turns of the input shaft, the output shaft turns once. So we're going to trade by a factor of 6 some speed for some force. And let me see if I can keep this in focus here. Check out how this works. I'm going to turn it slowly because I'm not sure how quickly the video is going to update. But for each turn of the input shaft, the output shaft will turn 1/6 of the time. And after every 6 turns of the input shaft, the output shaft will turn. And that's a hypocycloidal gear. Because of the math of the geometry, they're supposed to have less backlash than a planetary gear solution, and possibly even be a little bit stronger for the same materials. Now, I'm not doing this out of aluminum or brass or steel or anything, but what I'm hoping is that I can build something with enough backdrivability that I can use the current being inputted into the brushless motor to approximate how much force is being applied. This is all theoretical until I can actually get it to work without melting it. But hopefully this is coming across. You'll notice that the hypocycloidal gear isn't turning, it's just kind of rotating in place. And for every turn of the input shaft, the output shaft will turn 1/6 or 1/6 of 360 revolution. So that's what I'm aiming for.
Could you remind me backlash is?
Yeah. Oh, another. That's a good question. So in simulation, and I can show you on this because this is incomplete and I didn't print it out super well. And most gearboxes, if they are absolutely perfect, which none are, there is no play in the gearbox, meaning you can't wiggle it at all. All the positions are absolute, and if you know the position of the input shaft and the math of the gear reduction, you know to within, you know, infinite millionths of a degree what the position of the output shaft is. Now this is 3D printed, and it was 3D printed quickly, and I don't even have a bearing in here, so it's kind of sloppy. So I'm gonna hold the input shaft firmly with my right hand, and I'm going to, and then watch the indicator right here. So I'm holding everything firm. So technically, if there was zero play or zero backlash, nothing would move. But because of, well, I didn't print this very high quality, I'm able to, I don't know if you can make out that movement on the webcam or not, but there's a little bit of wiggle in there. That wiggle is called backlash, and that's the difference between input shaft and output shaft in slop or in, yeah, let's just call it gearbox slop.
Slop, yeah.
And so you'll get it in any mechanical system if you're doing Acme lead screws for CNC or anything like that. Backlash almost always comes into play, so you tend to account for it. And that's like, how much extra do I have to turn the input shaft before the output shaft starts to turn?
Excellent.
All right. All right, let me go ahead and switch back to, so now that you've seen what we're aiming for, let me go ahead and switch back to Fusion and show you.
Ellen, can you please fix the deal so you don't get the interruption of the video of the participants?
Oh, okay, so I think I've set that up on the recording, but as a, and that's another good question, another good point, is Zoom was designed to be primarily a collaborative interaction medium thingy. Meaning that it tends to focus on whoever's talking loudest. And if it's a conversation between multiple people, that's actually pretty awesome. But if you want to focus on one person or one person's video, just go ahead and click on their video with the right mouse button and select pin video. And that'll keep their video first and foremost on your screen. Now, as far as the recordings go, I've done something where I'm hoping that I remain front and center on the recordings, but I'm not sure yet.
Okay, thank you.
Yeah, no, thank you. Good question.
I was wondering if you, on your cycloidal gear, if you could take the inner gear there and make two of them and power difference between them with a spring like they do on planetary gears sometimes to achieve a zero backlash solution.
I would guess most of those solutions would also apply. The Paul Gould guy has done one or two things to reduce backlash. What I can share with you is that when comparing planetary gears with hypocycloidal gears, when manufactured correctly, hypocycloidal gears tend to have less backlash than the planetary gears. Plus, I think they'll be a little bit stronger. But I personally haven't finished one yet, so I guess we'll find out together. For sure.
We'll answer. Cut and dry.
All right.
Alan, what's your thought about the strength of the internal gears relative to this, you know, reverse backlash and stuff like that, or the torque, the back torque that it can handle before the gear itself might break with the materials that you're actually 3D printing with?
Mm-hmm. I need a mechanical engineer to back me up on this, but looking at the relative designs between planetary gears, which are smaller gears that are closer to the center of rotation, to hypocycloidal gears, which are larger and they're exerting a force farther away from the center of rotation. For the same material, hypocycloidal gears will be much, much stronger than planetary gears. But but you can't fit a hypocycloidal gear in the middle of like those MIT cheetahs. So it's for different applications. And I've seen some people that have tried to, or working on, tried means they may not have succeeded. They're creating planetary gear reduction versions of the same kind of gearbox. But my mechanical engineer spidey sense tells me that they're not going to be as strong as a hypocycloidal version. Plus, hypocycloidal sounds cooler.
Thank you.
All right.
Hey, Alan, have you done anything with like nylon gears instead of PLA or PETG or ABS?
Oh, you had to bring up the one material that I've never successfully printed. Here, let me show you something really quick. I'm going to grab it off my shelf. So some of you all from the Riverside or the Long Beach Club may recognize this. At some point, one of the printer companies released a file for a Ducati brake handle, and I said, "What a cool way to compare the characteristics of the different print materials." And so I went everything from a carbon fiber PLA, and I'll bring, as soon as we're allowed to meet in person, I'll bring this back so you can see it. It's a really fun example, because when you hit them on a table, the tone that each plastic produces tells you how strong, firm, how stiff it is. And each one of these materials will trade stiffness for flexibility, and the carbon fiber infused PLA has the highest tone, so it has the highest pitch dink when you dink it on the table. And it goes all the way back down from normal PLA to ABS to PETG. And each one of these brake handles is very well printed, not to pat myself on the back, except, and this is my fourth and best attempt, the the nylon version. I've been printing for what, 6 years now, and I still have not figured out how to print nylon. So that's the closest I've gotten. As far as materials for gearboxes and stuff, these gearboxes, brushless DC motors can get between 40 and 60 degrees Celsius. And some solutions, when you see on the internet, they'll actually use small cooling fans to keep things cooled down because the amount of power that's being pushed through them. So there's a very real possibility that these hypocycloidal 3D printed box designs will be thermally limited, meaning you can only put so much power through them before they melt. So, you know, you have to put less power than that. For the materials used, PLA is actually an incredibly good material to print gears out of. It's very, very stiff, but PLA has a phase transition temperature of about 40 degrees Celsius, which means that at about 40 Celsius, the plastic starts turning from a solid into a liquid. Not great when you're using motor drivers and brushless motors that can get that hot easily. So the samples that I've printed out today, for today, they're in PLA just because I'm playing with it. But when I do one for reals, I think I'm going to be using PETG because it has a phase transition temperature very similar to ABS, meaning I should be able to take it to 40 and even 60 degrees Celsius before it gets gooey. But I would love to, because Walter, that's a great point, to print these gears out in nylon, but I've never figured out how to print in nylon. Nothing I've printed has ever stuck to any build plate with any combination of goo or spray hair stuff or ABS or anything else. Have you seen anyone successfully print nylon? But I'd love to talk to them to find out how they did it.
I would love to try it if you have some spare nylon.
I do. Yeah, I've got 2 or 3 different types. It is extremely hydrophobic. So What that means is that and I'll pass it off to you as soon as we're allowed to meet in person again. You'll put it in the oven for a couple of hours to dry it out, because it's going to suck up enough moisture from the air to be impossible to print with over the course of an hour or two.
Wow.
So you dry it out, you set it up as best you can so that it not exposed to a lot of air. You'll print something and then you'll dry it out again for the next print. Yeah, I've got 2 types, and yeah, I'd be happy to see what you can make of it.
Yeah, don't you need a direct drive extruder for that?
Direct drives definitely help. You can do a Bowden, but the exit part of the Bowden, the interface between the end of the Bowden and the hot end, needs to be fully constrained.
Yeah.
Because if you don't, you get that bowing thing where it kind of pops out the side, like when you print with like a Ninja filament or Ninja Flex.
Yeah.
It just kind of pops out the side if it's not fully constrained between the Bowden and the hot end.
Yeah,
for sure.
So, Alan, another just quick material science question. When you're doing 3D printing, is there any kind of spool type of material that when it's actually 3D printed has metallic type of strength result, if you will, so that when you print a gear, it's more like a metallic gear rather than a fiber-like kind of gear? Do you have any idea about that kind of thing, which would endure higher temperatures as well as, you know, more long-lasting in terms of its strength and even accuracy?
Yep, so there's 2 answers to that question. I'm going to switch back to share screen here for a second to show you what I think I know about it. So for just something that looks metallic, there are, we're going to skip to that guy a little bit later. There are a couple of different filaments available that have a small amount of metal embedded into it. They're heavier. They polish up like brass or copper, or some other ones, or aluminum, but they're not really used for strength. It's just for looks. And let me see if I can find here. Let me switch forward onto this guy. So this is the stuff that like you and I would be able to get a hold of. Let me see if I can find an example of an output object. Oh my gosh, the talking head is not going to show us.
Because I'm thinking, some of these nanomaterials or something could wind up being, with carbon-based type stuff being very, very strong, but yet maybe 3D printable types of filaments of some sort.
Yep, and there are filaments that have embedded little chunks of carbon fiber, which are very strong and very stiff. But again, it all depends what you're using it for. Let me give you an example. Is when the carbon fiber filaments first became available to 3D printers, and they're still a little bit more expensive, but they were really expensive when they first came out. And they tend to tear up the inside of the brass nozzles for 3D printers. But the drone guys got super excited. Oh my gosh, I can 3D print my own drone frame. It's going to be super ultra stiff, and I'm going to be able to fly that everywhere, right? Makes sense.
Yeah, yeah.
So they did that. They bought up the filament. They designed and printed or printed out drone frames. Assembled all the electronics, put all the motors and propellers in, and then they started flying. In any material, there's going to be a trade-off between, and I always call it stiffness and bendability, because that makes the most intuitive sense to me.
Sure.
And carbon fiber infused PLA is extremely stiff. It holds its shape very, very well. When you tap it on the table, that tap tone that you get from it tells you that it is very stiff, which is super awesome. So you've got super accurate position of all the drone pieces, and that is perfect until you lose control and the drone drops. So
and kills somebody, or just simply cracks up?
yeah, so it drops, And that stiffness, because you've traded bendability for stiffness, there's no give in the frame. So the moment it hits the ground, it shatters.
Ah,
So when you're talking about strength, like I used to think about strength just being, you know, how resistant it is to bending, but there's always going to be this trade-off. Do you want something that's stiffer but less flexible and more likely to crack, or something that gives a little bit, so there's not, you have less guarantees that dimensionally it'll maintain the exact same shape to the micron, but is a little bit more tolerant of being bounced around or dropped. That's why I tend to like PETG. It trades a little bit of that stiffness for a lot of bendability.
so I'm thinking in terms of a gear tooth. You know, you'd want something that would not break from reverse pressure against it, let's say, or reverse force against it. But perhaps what you're saying is you want a little bit of give, maybe? I'm not sure what, you know, from a material or mechanical engineering standpoint would be the trade-off on that.
Yeah. I'm not, that's really isn't my background, but I'll observe that when you're setting up gearboxes, your two major choices are plastic or metal, but when they say plastic, they mean nylon. So when you're buying servos, generally the less expensive ones are called plastic gear servos with nylon gears inside. So they're not quite as strong, but a little bit more forgiving. But if you want something that's able to exert more force, you spend a few more bucks on the metal gear versions of those servos. To come back to the hypocycloidal area, if you were to machine hypocycloidal gears, those are, you know, going to be a lot stronger than the 3D printed ones. But when you're printing them out, there's actually a bit of discussion right now about, for gears, do you want the ultra stiff, and we'll eliminate chipped carbon fiber because that's so abrasive, no gearbox would last very long. When you're printing out gears for something like this, do you want your PLA gears, which are super stiff, which are actually excellent gear material because of that stiffness, as long as they don't get too hot? Or what I'm going to try to do is I'm going to see how well PETG printed gears, so it has some of the bendiness characteristics of nylon, a little bit more forgiveness, but maybe it's not quite as precise. It's one of the things I want to find out myself. I don't know the answer yet.
Well, thanks for exploring this. Appreciate it.
Oh yeah, my pleasure.
Things I observed with PETG is all the stringing. It's really hard to eliminate that. Yeah, for sure. You'll look at your it's a little bit more sensitive to print temperature, and that's tricky as well, because your print speed and your print temperature together will determine how strong the part is, right? How much time between layers you give that hot filament head and that hot filament to loosen the polymers on the layer below to interconnect to make a strong part. And so you think, okay, we'll print hotter, and you can print hotter and make a stronger part. But when you print hotter, the stuff strings like mad. So there's a balance point, a happy medium, or the lesser of two evils, depending on how you look at it, between print speed, print temperature, and stringiness to optimize for the characteristics that you're concerned about in your print. What I end up doing on mine is I'm going for strength first. So I'll try to find the lowest temperature and the highest speed that I can print at that gives me the strength that I want. And if I'm lucky, it doesn't do a lot of stringing. I think I actually cleaned up a lot of my string. That would have been a great thing for me to not clean up before the talk. But one of the things that I do when I get a part out, here's an earlier version of the outside ring, is I'll just pick out all the strings that I can with my hands, with my fingers, and then a quick second over an open flame will burn away the rest of them up to a point. But yeah, Les, you're absolutely right. That's the trade-off. And from where I'm sitting, it's like, do you want something pretty? You know, do I want something pretty, or do I want something strong? And usually I go for strong, and I just try to clean it up. Well, I also saw recently a new SLA printer, which does an epoxy. It's a UV tempered epoxy. Mm-hmm. And it's really, they reduced the price a lot. It's $2,500. And I was wondering how the epoxy would do for gear gearing, at least as the core of the gear. You might have to put some surface on it.
So if it's the same type of SLA that I'm familiar with, the resin printers, they do have some tougher resins, but they're not really suitable for structural or gear materials that I've seen. You can prototype the shapes in it, but they don't seem to have the wear or durability of 3D printed or molded plastics.
That's what I heard too. Yeah.
Yeah, and they're coming down in price. You can get an introductory resin printer for like $300, maybe even less now. And
Yep.
they have some big ones. If I don't know how. I've been looking for an excuse for like 2 or 3 years to buy a resin printer because the technology is so awesome and you can do such detailed, intricate prints. Of course, the resin's toxic, and if you touch it more than 3 times, you have a severe reaction. But I just haven't found a use case in the stuff that I do to make use of it so far, including the behemoth of a printer that I bought after Walter did. I've been able to get everything done that I need to using 3D printing.
Oh, that's right. You have that CR10.
I do. Yeah, it's almost fully
Nice.
assembled now.
Wow.
One of these days I'll finish it and I'll have something big to print out. Yeah, you're a little bit ahead of me on the huge 3D print space. I have a little bit of catching up to do.
I've gone through like 3 print heads already on mine, extruders. One last thing about PETG. I've been doing some PETG printing for like 2 weeks now. And the thing that I found is that if I reduce the retraction length, I don't get any more strings.
I was going to
So
mention that because I've had to read up on, stringing a long time ago, and one of the key things was retraction as
yep.
well.
Yeah, it makes sense. So I tried it, and lo and behold, my prints are really nice in PETG now.
Oh, excellent.
Yeah.
Yeah, it's a little bit finickier, and it's a lot harder to paint and finish. But from a durability, that ratio between stiffness and bendability, I'm loving it. Plus, they've got some really bright, yellows and oranges and greens, and you know how I am with the loud and proud colors. So, it's shirt notwithstanding. All right.
Lots of 3D experts.
All right. So to kind of wrap up the talk on Fusion, we kind of went off on a couple of different tangents. Sorry about that. Let me switch back to the screen here.
What else we do?
And what I wanted to show you was symmetry, employing patterns in your designs to save time. Now, I'm going to skip forward a little bit on this one. I'm going to say my reference diameter for the gearbox is 50 millimeters in diameter. And we're going to call that reference diameter, just so I can remind myself of how big the gearbox is supposed to be. From there, I'm going to, let me save the design. We'll call this RSSC gearbox tutorial. And I'm going to create a new component. This is going to be for the gear, and that'll be made active. Now, so what I have here is a project, and what I've done in that project is I've created a new component in that project, and I've made that project active. So that means that everything I'm doing is gear related. It's a way of organizing your work when you're doing something complicated with multiple parts. Now, let's go back over to my gearbox generator. Now, this is the gearbox I'm currently working on. These are parameters that I've already set up. I've, from a couple of iterations, I know that I want the centers of these posts to be 24 millimeters away because that fits in my 50 millimeter frame. I know that I want each post to be 10 millimeters in diameter or 5 millimeters in radius. It's a 6-to-1 gear reduction, so there should be 7 of these posts and 6 lobes in the gear. And as you change these around, it redraws the gear in real time, which is super awesome to see what these things are look like, way faster than going through and hand drawing them. So what I'll do is I'll export that design. I'm going to call that RSSC just for sake of the demo. And it's going to export that design as a DXF or a drawing type file. And from there, in our gear, let's go ahead and expose the origin and do a new sketch. And in this sketch, let me move some things around so I can see them over here. There we go. We're going to insert that DXF file that we just generated. So I'll go back over here. Hopefully I'll remember where I stuck it. And it's going to pause for a second as it crunches it. There's lots of individual line segments. It takes a couple of seconds for it to import everything. I get a warning that the DXF file is unitless. It doesn't contain units. So it's like, I think it's millimeters, but let's see. And here we have an import of that DXF file. Now I want to point something out to you because sometimes it works and sometimes it doesn't. Now, when you cursor over a closed solid, let's see, I think we want it just like that. I'm going to go ahead and click on OK. And after a couple of seconds, it'll fully import that DXF reference file into this drawing, into this sketch. Now it's still chewing on it because it's a really inefficient way of getting it in here, but this is great because this gets us about most of the way of where we need to be. All right, so I'm going to turn off that reference diameter circle for a minute. Now, when there's a closed shape and you put your cursor over it, it'll change color. That means that this is a closed circle. In theory, we could extrude it and it would be a solid. Fantastic. We actually can't use these because even though they look like circles, they're not imported as circles, so we'll ignore those. But check this out. When I put my cursor over the gear profile, that doesn't happen. And that doesn't happen because it's actually made up of several thousand small line segments, and there's an open segment somewhere. So I can't extrude this. I can't directly use this shape to design a part to 3D print to create my gearbox. But that's okay because we are getting better at Fusion 360, and there's some things that we can do to work around that. So I'm going to call this sketch where we imported that file, let me call it reference gear profile because it sounds cool. And so that's going to be a sketch underneath the gear. And same thing, you can see that I could, in theory, extrude each of these circles, but I can't extrude the gear ratio. So let's talk about patterns. 7 minutes before the end of the talk, the main focus of the talk. Let's go ahead and create another sketch. So this is a different sketch from, we'll go ahead and turn the other sketch off. So we have this reference sketch with some stuff on it, and then we have our new sketch 5. This sketch 5 is going to be our actual gear profile. And we're going to use patterns to recreate that gear without drawing several 100,000 points or whatever it is around the entire gear. So what do we know? We know that this gear is a 6-to-1 gear reduction, which means that the gear on the inside has can be divided into 6 equal pieces. So if we reproduce 1/6 of that, we could then use a pattern feature to get the rest of it. So that's what we're going to do. I also noticed that as I put my cursor over that line, I've got these guiding dots for the beginning and end of each line segment. We can actually use that also to reproduce or project those dots to get the gear. So these are all the pieces we have. Let me show you how I can use these tools to actually reproduce the gear. So I always say start with what you know. So we'll leave this gear visible. Now I'm going to draw a reference line. I'm just going to draw it up about this far. It's going to be a vertical line. Doesn't matter how tall it is as long as it goes all the way to the top. Now I'm going to make this a construction line. What that means is that I can't use it to extrude anything there. It's just there for reference. And by default, when I drew that, Fusion was smart enough to say, oh, you drew this line straight up. You must have wanted that to be a vertical line, so it'll apply a vertical constraint to it automatically, meaning I can just change the length of it, but I can't move it anywhere else because of that constraint. So that's some of the things that are happening that you get for free when you draw a line that's straight up and down. So I'm going to do a second line out at some random angle as long as it's larger than the gear. And I'm also going to make that a construction line. And I'm going to define a relationship between these two lines. So I'm going to hit D for dimension. Line 1 was already selected. I'm going to hit line 2. And I want to define what the angle is between these two lines. Now, I actually know what the answer is supposed to be, but that's because I've done this a couple of times. I know I want 1/6 of 360 degrees, right? So 360 degrees is an entire circle. This has 6 lobes on it. I want 1/6 of that. So you could either grab a calculator or just type in 360 divided by 6. And eyeballing it, it looks like this is at the center of this lobe. This is at the center of that lobe. So I think we've got a good start. Now the next tool I'm going to use is, let me embiggen this a little bit so we can get a better look at this section of it. There we go. I'm going to use the Fit Spline tool. And what I'm going to do is I'm going to grab, oh, sorry. We're going to do one more thing. Those lines in blue are lines that are showing forward from a different sketch. I actually want to grab some points from that to recreate the curve. So in order to do that, I'm going to use a feature called project. And what I'm going to do is I'm going to say, I don't want the entire line projected, but I want some of the dots projected so I can reproduce the curve. So I'm going to really quickly, I'm a little bit more careful than this when this might be off by a couple of microns, but you get the idea. I'll grab like 6 or 8 or 10 or 20. Project these points from that reference sketch. Let's grab that and that. So we're going to project those points from that reference sketch onto my new sketch. And once that's done, I can get rid of the reference sketch. And we've got this rough profile of some points that approximate that curve that we want. Now I'm going to use that spline tool, and I'm just going to go in and I'm going to connect the dots. And as I do this, the spline tool is going to approximate the curvature required to create a smooth transition from one point to the next. So it's not going to be absolutely perfect. The resulting curve will probably be off by a couple of microns, but that's okay because my printer is only accurate to about 100 microns. And we're doing all of this because the imported shape was not a closed figure. All right, so now we have a line. Not too useful yet, moving my cursor around. We don't have any closed shapes that we can extrude. But now that we have 1/6 of that profile, we can select it and go over to the Create menu, and we can create a circular pattern. So we'll select that. It needs to know 2 things. It wants to know what the center point is, so I'll just select the center of the origin of the sketch. And it wants to know what I want to repeat in a circular pattern, so I'll carefully select this profile. And when I do that, you can see a couple of things happen. It's like, okay, well, you want to complete a complete circle, here's what I've got for you. So it says full, and it is creating 3 copies so far. So there's one right there, one right there, and one right there. That doesn't get us all the way there because we know that we have 6 lobes. So let's change that quantity from 3 to 6, 4 to 5, almost there, and a 6. And if we did everything right, if this line segment began and ended exactly on the 60-degree mark, and that represented 1/6 of the lobe, and we reproduce it 6 times, Fusion 360 should be smart enough to connect the dots and create a solid. And as you can see, when I move my cursor over the resulting circular pattern, Fusion 360 recognizes this as a potential solid, a closed sketch, and I can then extrude it into a shape. And depending on how much time we were going to take, there was a whole bunch of other stuff I could bore you with. But for right now, let's just give this a hub. And my bearings that I'm using are 18 millimeters in diameter. So let's mark this one off as an 18 millimeters. And let's use that circular pattern one more time. I'm going to draw another circle. It'll snap to the center line. Let's just draw it to some random thing. Let's call this one a diameter of 8. And we'll grab that feature, sorry, not that feature, that sketch entity right there. Click on Create, Circular Pattern. For objects, because I already selected it, it says one selected. We'll move over to center point. I want it to rotate around the center or the origin. And let's do it in front of every lobe again. Let's do 4, 5, and 6. And you'll notice that this profile now looks very similar to the gears that I printed out. Now, and this is something it's intuition and experience, right? When you're going through and creating and designing things, if there's only 2 parts to it, you could always just brute forces it and put them in individually. And when people are first getting started in Fusion 360, they may individually define, 6 different lead lines and draw 6 different circles and define each of these because they knew they needed 6 and what their ratios were. And that totally works. But once you know there are tools out there like rectangular pattern and circular pattern, you can save a whole bunch of time by only creating or recreating the geometry that you absolutely have to, and then using those tools to fill in the blanks for you. So now when I put my cursor over this, everything turns shaded. That means that it's potentially a solid. I can click on Finish Sketch and then cursor over. We still get that opaque, meaning that we could extrude this if we wanted to. I'll right click and select Press Pull. And once you do that, you can grab the bars to move things up or down. I happen to know that I want this gear to be 5 millimeters tall. So I could either drag this to 5, or if you know the number in advance, you can just type it in. And then hit OK, and bada bing, bada boom. You have a cycloidal gear that was sourced from an imported DXF file. That DXF file was incomplete, but it had enough information that we could reproduce it by using some of those points as a reference. And this is exactly how I created, extruded, and then exported and printed out the cycloidal gears that I showed you in the gearbox I did earlier. So that's how far I've gotten so far. I've got some more tweaks to the toolbox, and eventually I have to get to the electronics. But I'm fairly excited to see when I get this done, how strong it'll be, and how strong it'll be not only based on the materials that I'm using, but also the limits to the power that I can push through it, knowing that even with PETG, I probably can't exceed 60 degrees of temperature for the driver board or for the brushless motor. The other thing that I haven't seen a lot of information on the interwebs is that these brushless motors, let me go ahead and switch back to camera here view as we wrap this up. These guys are designed to have a rotor attached to it. And that rotor, pushes air and that lifts up the drone. But that rotor also pushes a large amount of air through the motor as it flies. Perfect, elegant, beautiful design for drone motors and rotors that self-cool. Well, when you're using these for robotics, the only airflow you get is the turbulence from these little tines right here. So I'm really curious to see how hard or easy it is to keep these things within temperature based on the amount of power you push through it.
Oh, that's amazing.
So that's what I've got so far.
I'm sure you can design something
right
to
now.
blow into it.
Huh?
They're pretty open. I'm sure you can design something to blow air into it.
Yeah, and there is a couple of designs similar to the MIT Cheetah where they've actually crafted a small 40 to 60 millimeter fan whose only job is just to blow air over it to keep things cool. I have an idea about that though. And you know, robots tend to hold perfectly still, right? You move to a position and then you stop. Now
Yeah.
it's that stopping that's the biggest problem, because when it stopped, you're applying power to the motor to maintain that position.
Yeah.
There's nothing to dissipate the heat buildup because there's nothing moving. Now I wonder if you program something so that instead of holding perfectly still, what if you got a little bit shifty? What if, you know, every half second or so you just moved a half degree? If that would be enough to keep the temperature within spec. That's one of the other things that I'm wondering about, is to have like a fidgety robot that doesn't hold perfectly still.
That gives it a more organic feel anyway. That's like a goal in robotics.
Yeah, I think so. I think it's going to be fun.
Is this the
It
thing
generates.
that, sorry. Is this the thing that you were saying you needed 12 of? Or is that something different?
At least. You need a minimum of 3 of these per leg. And if you're doing a quadruped, that's 12. And then if you want to go extra with like an articulated neck or tail, you could go as high as 16 or 18.
Oh, okay.
And the good news is, because we have Fusion 360 and tools like this, I don't have to build it with my hands to figure out if it's going to work. As I make changes to the gearbox, what I'll do is I'll mock it up just to see how things will play out. Now, this design I'm showing you, I'm not super excited about. It's just my version of doodling. But to take a simplified version of those boxes and then to insert them in the model and say, okay, if I were to build this, would there be enough room? What would it look like? What would the shape look like? Fusion 360 makes these kinds of analysis and doodling really easy. And the more I look at this, as cool as it looks, the less excited I get, because this type of robot and design has been done a lot. But you know, you never know. The gearbox that I'm making right now is pretty small, so maybe it'd be fun to do a small version of it that was, you know, cheaper than $12,000. And so those are kinds of things that get me excited about building things out, not to follow someone else's footsteps, but to try something a little bit new. And a small version of this quadruped, something that's you know, bigger than the Todds I've been building, but small enough to make it within reach and within budget for more people. That's something that kind of gets me excited about continuing forward with projects like this.
Did James Burton, did he use linear actuators, right?
Yeah, so for those of you who aren't already idolizing James Bruton from XRobots UK, you should. He is working on another version of a quadruped. If you guys would like to stay on for another minute, I'll kind of walk you through what he's doing so far. Let's see, James Bruton. As you can see, I may have searched for him once or twice.
Oh,
You see
share your screen.
Oh, it's always some mundane detail like clicking on the share button. Sorry about that.
Have you looked at using one like Proto Labs to injection mold your device?
You know, I haven't looked at them for the robots that I'm working on, but I did look at them when I had briefly thought about mass producing plastic cases for the Raspberry Pi 0 and 0W. And I did submit some designs and get a couple of quotes for it. And you end up spending a whole bunch of money to have the cast machine. And then depending on if you're doing small or large scale, the cast, the molds less or more. And then they charge you by, not by print, but by part, depending on your production run. I haven't really imagined doing anything in large enough scale to where that would make sense. And that's about as far as I got. I know the larger the molds are, the more expensive they are. But how
Oh,
cool
yeah, the
would that
tooling on
be?
that is expensive. They
Huh?
actually make metal tools to put together. Some of my customers do that, and I go to the shop to work on their machines, and they got that stuff there, and it's like, you know, you should see it. And all that stuff was made and cut out, and so there's a lot of tooling costs just to have something made by plastic.
Yeah, and there's a lot of stuff. If you want to get the design right the first time, there's a whole bunch of rules on how to design 3D, not 3D printed, sorry, injection molded parts so that they can be molded successfully and pop out of the mold. And there's different prices for the molds based on the finish quality, if you want a mirror finish or a rough cut. But one of the things that I kept hearing about when I was looking through this was, when you're designing it, when in doubt, design it smaller than you expect, because it is far cheaper to pay them to rework the mold to machine out additional material than to try to add material back in, if it's even possible, if you design something too big. And that's all I think I know about it so far. But how cool would it be to design something with enough reusable parts, like, you know, Todd or something else, to where it would make sense to go in on a production run of like parts for the entire club or something? That would be fun.
I was thinking though, for your motors and the gearboxes, if you've got 12 per robot and you get 10 or 12 of us to go into that, maybe that would work out to be a quantity suitable enough to injection mold.
You know what? It would be a fun thing to explore. So what we could do is, we could do this as a forum post, or, you know, when we're back in person, we could take an example of the gear design, because you've already heard I have never been able to print in nylon. And if we decided that nylon gears were the way to go, and I finally designed something super awesome that we all wanted to go in on, we could go through the process of uploading the design and getting a quote from Proto Labs to see if it would make sense, for sure.
Just a thought, because I was thinking, since it was something you have so many of in one robot, that might work out.
Yeah, that would be super cool if one of us designed something, you know, that worked well enough that we're like, everyone needs to build one. We'll see how close I can get on this one. Let me switch back to screen share just for a moment. James Bruton has been doing something very interesting. Well, he always does. Let me switch back over here. So he is designing yet another super awesome robot. I'm going to pause it right here. After his big dog, he is building something smaller. And he's actually using standard Metal Gear servos. In earlier videos, you can actually see in the frame where he's using a standard Metal Gear servo, and then using a 3D printed 2-to-1 gear reduction to make these things strong enough to move around a beast like this. Now, before the brushless motors and the 6-to-1 planetary gears and current sensing, in the 80s, the MIT lab patented a different solution to this called series elastic actuation. And what that means is that they would insert a spring between your output shaft and the actual output, and then they could use spring constant and measure spring deflection to approximate how much force is being applied. So you have more moving parts, but you can do it with materials that were available in the day. What James is doing right now is something very similar to that. Now, I'm not 100% if he can detect force unidirectionally or bidirectionally, but what he's done is he's attached the output shaft of the arm to a spring, and he's using a Hall effect sensor to measure the spring deflection as force is applied to the leg. Now, theoretically, this would allow him to do all kinds of really exciting and interesting calculations about force, motion, and acceleration, and how they apply to movement strategies. And there's an earlier clip. I highly recommend you watch through it. They're really great, with the yellow version of his mini dog, where he goes through that. So he's working on a walking solution that has active feedback based on the forces applied, and I'm excited to see how close he gets with this. So when you go with far higher gear ratios because of that backlash and that, like, we'll just call it friction in the gearbox, by adding in a spring to the output shaft, you can do something similar with some more sensors, another sensor, spring, and some more mechanics to help approximate the force that's being applied as you move your leg or your arm through space. It's a very cool project. For sure. All right.
Alan, if you're, what's the main, I mean, the main reason that you want to know the forces? I mean, a lot of our robots, I guess we don't know the force. We just, we measure how much it moved and then adjust from there. So it's a walking, is it particularly important with walking or robots or with that you know the physics?
Yeah, I would say it's more than important. I'd say it's required. So in the, let's call it the evolution of hobby robots. In the beginning, you have servos, right? So cheap boxes, you've got 3 wires, power, ground, and signal. The signal is a PWM pulse between 1,000 and 2,000 microseconds.
Milliseconds.
And oh, thank you. Yep. And so that pulse is sent to the servo motor, and that pulse represents a command. I want you to move to what I assume this position is as quickly as you can, right? And so we say these servos operate open loop with respect to their input, meaning I've got this servo, I'm sending it a pulse, but once I send that pulse, I have no idea what position it's currently in, how far away it is from the goal, how fast it's moving, how much force it's applying. It operates open loop, right? Now internally in the servo motor itself operates closed loop with respect to its input angle and where it's at. So it looks at the error between the command angle and the current angle, and it closes that using a PID loop to get in there. But as a user, you have no control over that PID loop, the acceleration deceleration curve, if getting there is faster than stopping on time. But you can do a lot of cool stuff with it. There is a whole wrestling robot league of servo bots that you can drive around with radio control and, you know, punch each other and stuff. So it is really fun. But that's kind of stretching the limit of what you could call a robot, because they're really just reproducing actions, and there's zero knowledge in the device about where it's at, where it's moving to, why it's moving there, even the position. It's just replaying motions, right? So one of the things I did a few years ago, I said, okay, well, that's fun. Can we modify servos to make them more useful? So I took a lead from the center pole of the pot that's in the servo, and I carried it out to an ADC. I said, okay, well, it's not accurate, but now I can more or less sense my the position of the servo. And this is a calibrated value. There's lots of magic numbers based on the voltage that's coming out of that. And we say, okay, when the voltage is this, you must be at 0 degrees. And when the voltage is this, you must be at 180 degrees. And, you know, hopefully fractionally anything between that will tell me the angle. But it's not perfect for a bunch of reasons. But that's the first step. We'll call it proprioception. The device's ability to know its position in real time. And with just position and high enough sampling, that gives you all kinds of information about not only where you are right now, you can actually come up with your own motion plan about how to get from point to point B in terms of acceleration and speed. You can sample over time, and you can, it's not first, second order derivative, but you can measure, and the distance between angles and time, you can interpret the speed and the acceleration, or the change in speed over time. So you have all this rich information you can use to characterize the behavior of the bot. And in the 3D model, you can even approximate how heavy your components are in like RViz or Gazebo. But but you still don't know how much force you're applying. So all of your control is positional. You know, I want to move to this position, I want to move to here. And it's closer, and there's a lot of fun stuff you can do. But what happens when instead of saying, I want to be here, I want to apply a force of 1 Newton in this direction, right? So unless you have some type of active force feedback that's sensitive enough to be able to sense the types of forces that you need to know about, then you're still kind of operating open loop. And it's hard to do. There's not a lot of equipment out there to do that. This MIT Cheetah with the low gear ratio and the current sensing is probably the closest they've been able to do to get it reliably. Series elastic actuation has been available since the 80s, measuring the spring deflection to approximate the force applied. I never really saw anyone do anything super useful and precise with it, so I'm really excited to see what James does it with him. But in my opinion, until you have all that information, position and force, you really don't know, the robot has no way of knowing what it's doing, and there's no way to apply any motion control strategies or control authority that takes that into account.
I would add, Alan, just one minor thing, and that is that if you're dealing with arms that have to lift in an industrial or other kind of setting, you'd probably want to know whether a package you're lifting would be either too heavy or whether it's light enough to actually have this particular robotic device actually be able to lift it and move it around. That would be an important area where you would have to somehow detect the weight or the mass of the object that you're actually interacting with. And as humans, we do it naturally with our muscle and neural system computations that are just embedded in us. So yes, to have this kind of measurement ability in a robot to measure forces, somehow that would be an important parameter or measurement to be able to make. And I'm sure there are many, many other applications other than just lifting packages and stuff like that.
Oh yeah, it's literally, it helps us as humans determine how we interact with the world. Now it's not really a contrived example, but it's a very real one. How do you get a robot to pick up a glass without breaking it, or the egg test, right? And so this is why you see in every manipulator function, except for ones that are specifically showing pressure, sensitivity, or force feedback, they're always plastic. And that's because without any force feedback, there's no way for you to know that you have squeezed hard enough or too hard. And I think as force feedback becomes more available, this is the last frontier in that bridge between the physicality of building robots and programming them. And I think even with the Spot Mini and the MIT Cheetah, with the motion planning and the gates and thing you're seeing with them, they're taking the mass of the motors into account computationally, and they're taking the forces applied into account as they move. And so what you're seeing now is some really, I don't want to say totally natural, but much more natural motion strategies that take into account the mechanics of the beast and aren't just like a rigid Asimo walking like an old person, statically stable, step by step. That's the way I see it.
Well, wouldn't that, sorry, hello, Alan.
Hey.
Yes. Wouldn't that make the servos work less then, or the motors, I should say, rather?
Yeah, it potentially can. And there's one more thing I want to show you before we wrap up. I know we've talked about it a couple of times, but on YouTube, I'm only stalling because I can't remember. Oh, MIT, of course it's MIT. MIT, this super sharp guy that has this awesome haircut just like me, has been publishing a course called Under Actuated Robotics. And I'll be honest, I can get about 10 minutes into the first class before the math is lost on me. But when you have knowledge of the force you need to apply or the force you're applying, you can use that to do and this is under actuated robotics. I think a couple of us have watched through it. I'm probably someone other than me has understood a lot of it. You can take that into account so that you don't brute force the position, because all control authorities and control strategies for servos and above, you're just commanding to a position. Get there as wasteful as possible with as much energy as you need and stay there. And any control strategy that takes into account the dynamics of the robot, the weight of the legs, the force you need to apply, can get the same result with a lot less power, like 1/10 the power, probably even less. Right? Because you look at like when you walk, you don't walk like an Asimo robot with each muscle rigidly held as you are statically stable to the next, like an older person who's afraid of falling, right? When you walk, it's basically controlled falling. You throw your center of balance forward and your leg catches you before you topple forward. It's a very low power operation when you're walking on a level, perfectly flat thing. And once you have access to that force information, that kind of stuff becomes trivial, easy, for sure. All right, we went really long today. I'm really sorry about that, but this was a great discussion. What else is going on? How's everyone else doing?
Doing good.
Terrific. Even though you feel that we've gone long, we've covered a lot of really important material, in my opinion, Alan, and you did a great job tonight. Thank you very, very much.
Yeah, I always appreciate the Fusion 360 tips and stuff, because there's just so much to know about it that I don't know. Maybe a lot of people don't. I don't know.
Yeah, and I'm not an expert by any means, but I'm happy to share anything I've picked up over time. Like on my Todd project, my whole goal was to level up a bit. And every time I get like something new under my belt for learning, I see a whole other set or area of things that I haven't even touched on yet. So it's been fun. It's a great tool. It's still available for free for students, educators, and for anyone who makes less than $100,000 in a year directly through the use of the software. I ended up supporting them last year. I bought a license because it was available at like 60% off, just because it's something that, it's going to sound corny, but it brings me joy. I truly enjoy learning and using the program, and I want to pay that back to the company and the people that made that possible.
That's awesome.
Alan, what is the name of that professor that you showed where within 5 minutes the math is over your
Here, let me share the screen again and I'll show you.
Let's not sell him short.
No, I have tried to watch it for 3 years, and for 3 years I get 10 minutes into the first, so I'm like, I'm out, I need to get back to school.
Even his name on the board looks like an equation there.
Math is my second language instead of Spanish. Spanish used to be my second language. Is that?
So no, let me bebop back over to the website here. He's published the schedule. His name is here somewhere. He is super smart, and I am not finding. There we go. Russ Tedrick, and if you Google keyword search on YouTube under actuated robotics, you'll find his channel, and he publishes his lecture series every semester.
Oh, that's great. Thank you.
Oh, yeah, you're welcome. All right, anything else before we wrap up for the week?
No, just remember, every other week now.
All right, so we'll line up a speaker for 2 weeks from now. We'll send out all of the invites and information over the next week. If anyone is working on anything fun and you want to spend some time telling us about it, no pressure, but we'd love to hear about it as a lecture or a talk in one of our future ones. I don't know if it's obvious, but we're still supporting show and tell. So if you're working on something and want to spend a few minutes to show us, again, I apologize for going super long this time. During our next meeting, just get a quick video of it. Think about, within about 5 minutes or so, what you want to share about it. And it's just like show and tell in person. It's from the comfort of your own home. So something to think about for next time we get together.
Okay.
I might share on
Alright.
my remotes.
Sorry, Robert?
I might share one of my remotes, the sound portion of it. I know I did it. I did it once at one of the, actually a couple different club meetings, but those other people haven't seen it yet, so I think they'd like it.
Oh, for sure. Yeah, I'd love to see that next time. All right. Thanks everyone for hanging out. We'll see you in 2 weeks.
All right.
See you later.
And Alan.
All right. Thank you.
Excellent.
Bye.
Bye-bye.
Hi,
See ya.
Walter.
Hey, how's it going?
Good.
We'll see you. We'll see you around.
Okay.
All right. Bye.